put them here. So any questions from homework problems? No? Okay. All right. Okay. Then. Yeah. I hope actually you will ask some questions because this chapter 7 is relatively short. Okay, but here we still have to arrange this for a 2-hour class for this chapter, just because don't want to break up this chapter 8. So that's why this, relatively speaking, will be more than an hour, but it's not probably going to be 2 hours. Okay, so ask questions if you have actually for the previous chapters, or if you don't, of course, then I will start to talk about this chapter 7. Okay, so this chapter 7, okay, again, on the first slide, just show you what terminology, okay, you are going to encounter in this chapter. So you will encounter this the flux and the reciprocity. Okay, the comeback signal of MRI. Okay, you have a flavor about that, and then demodulation, and then the relative signal strength. Okay, well, actually, at the end there's also something about the RF coil, but we'll worry about that later. Okay, so what's going on in this chapter? Okay, so even before I start to talk about this, okay, just give you an idea. Okay, I said in chapter 2 and chapter 3, well, actually we should say chapter 3. In chapter 3, we're talking about transmitting coil. Okay, we're talking how you can actually manipulate spins. In this chapter, we're going to talk about how we can actually detect these signals. Okay? Now, this is actually important. Okay, it's probably hard for those of you who just actually say, okay, learn MR the first time. Okay, but let me actually to say this and then just try to put this together in your mind. So in chapter 3, we basically say, okay, at the very beginning in chapter 2, we say, okay, I have a main field pointing this way. We have spins, okay, a whole bunch of spins, and line up along the main direction. Okay, just assume that I'm talking about classical picture. Okay, don't worry about the quantum mechanics. So I have these 5 spins pointing up along this main field direction. Okay, and then of course you say, okay, if they have a little bit angle compared to the main field direction, then these guys are going to precess, right? According to what you have learned in chapter 2. All right, but let's just say these 5 spins really pointing themselves along the z direction, along the field direction. So they are not even precessing. Okay, they just stay like that. Okay, the next thing is you say, okay, in chapter 3 you apply a B1 field, the RF field, pointing, say, in this direction. Okay, it's not really this direction, okay, because we have said in chapter 3, if you have this B1 field, which also actually has to rotate at this lambda frequency. Okay, so at this lambda frequency, so rotating at this lambda frequency allows us to put ourselves in the rotating frame. So in the rotating frame, this B1 field is just actually pointing to, say, the x prime direction. So like this. Okay, so assume we are now in the rotating frame, and this B1 field is pointing this way. Okay, now what's happening to these spins? So these spins are going to precess again, around the clockwise direction. Where I say, okay, we just flip these spins, or we rotate these spins. Okay, so these are different verbs, but basically mean the same thing. So you rotate these spins onto the transverse plane, and at that point you can turn off your RF field. Okay, after you turn off your RF field, now you put yourself in the laboratory frame. Then again, well, okay, even in the rotating frame, it's the same thing. You are going to see these 5 spins precess clockwise this way, okay? Because you have a main field pointing this way, you have these guys actually moving like this. Okay, so the purpose of this RF coil, or say this RF field, is what we call a transmitting coil, meaning that, or transmitting field, meaning that the purpose is to flip or say rotate or process these 5 spins or a whole bunch of spins onto the transverse plane. Okay, now it's not necessary to really say rotate these spins onto the transverse plane. If you just rotate these spins at some angle, say this way, okay, so again, this is your main field direction, you flip these spins at some angle, say angle theta, away from this main field direction. Okay, then you just need to calculate the tangential component, or say the transverse component of these whole bunch of spins, right? So you know the answer. So if the main field goes this way, you have a whole bunch of spins pointing this direction, and the angle is theta, then the transverse component is basically what? Basically it's sine theta. Okay. That's basically the magnitude of the magnetizations of these 5 spins. Okay, so this is the purpose of the transmitting coil or the transmitting RF field, but then you have to turn it off. Okay, if you don't turn it off, then of course these spins or a whole bunch of spins, you will preset, you will rotate. Of course, just keep going. Okay, keep going until you turn off the RF field. If you don't, just keep going. So at some point you turn it off. So when these spins are on the transverse plane, or if you don't want to get, say, the maximum signal from these spins, you say, okay, these spins rotate at this angle, at this flip angle. You turn off this RF field. All right, then in the laboratory frame, these guys will preset like that. Okay, and then the next thing is, then you say, okay, now how am I going to pick up the signals from these, say, 5 spins? Okay, so this is the topic in this chapter. Okay, so the first thing is we have to talk about this Faraday induction. Okay, so before we really say, okay, what's going on, how we can pick up actually the signals from these spins. Okay, so the Faraday induction is this. So if we have a magnet and I have just a coil here, okay, so this is a coil where you say, oh, this is just a loop of wire. Okay, that's fine. And a loop of wire, in fact, is a coil. And then now I have this bar magnet. I just move this bar magnet actually to here. So let's say the first thing is that I move the bar magnet to here and it stop. Okay, just stop. And then the first thing you know is that okay, this bar magnet is going to produce magnetic field. And so this magnetic field, of course, goes to infinity. Okay, it's just, of course, the further away from this bar magnet, the field becomes weaker. Then, okay, but if I just have if I didn't move this bar magnet, and if this bar magnet just stays like that, then there will be no current induced in this loop. So nothing is really happening except that I have the bar magnet and I have a static field distribution in the space. Okay, but I do have actually that flux. Okay, I do have this flux, and by definition, the flux just means that the B field, the amount of B field through this area defined by the loop. Okay, so then in terms of the equation, it's just the integral of the B field, and then you have to do inner product with the normal component of the surface. I mean, it's really not the surface of the coil, but it's actually the surface of the area, or say the area defined by this loop. Okay, so you do have the flux. Okay. Now the next thing is you say, okay, nothing really is happening from this coil or from the loop. Okay, so then next thing you imagine that now we just actually move this bar magnet. So let's say we move this toward one direction. Okay, so just move this way. Even if you just have a constant movement, okay, now actually we create one thing. So now actually this flux, okay, just by the definition of the second bullet, now this flux becomes a function of time. So it changes as a function of time. Now when that happens, and all of a sudden actually, so Faraday basically discovered that, okay, actually then there is voltage. And so you measure the voltage across this loop, and then he discovered that, there is actually a voltage measured from this loop, from this circuit. Okay? And that voltage is called the electromotive force. Okay, so this is kind of funny, right? You say, is that a force? Okay, no, it's not a force in today's definition. It's a voltage. It's an induced voltage. Okay, so then at that time they just wrote down this equation. Okay, so that voltage, and it's called EMF, and this EMF is defined as minus d phi dt. Phi is the flux in the second bullet, and say, okay, so that's the induced voltage. So that's what they discovered. Okay, now what's important is also actually that minus sign in the definition of this EMF. Okay, now that minus sign is actually given by the Lenz's law. Okay, so then what's Lenz's law? Well, Lenz's law basically says if you have a field distribution like this and you move this bar magnet toward this loop, this circuit will have an induced voltage. Okay, so it has an induced voltage, then of course it has an induced current. But this induced current, in fact, will be in a direction such that the magnetic field produced by the induced current is in the opposite direction toward the fields you are bringing in. So now, of course, that's kind of obvious. It has to be this way. I mean, it has to be this way, right? Because otherwise, if it's the other way, meaning that if you bring in a changing field and then you induce the current, and such that actually the induced current flowing in the direction, of course, the induced current is going to produce another field, and if that field will just add up on the original, this external fields you are bringing in, so you just keep adding the field and then just making this current stronger and stronger. Okay, it's not going to happen that way. Okay, nature doesn't work that way. I mean, you're not going to produce energy from nothing. I mean, this, unless we're really talking about quantum mechanics. Okay, but it's in classical world, it doesn't happen that way. So that's why that negative sign is important. All right, and then so now let's say we have the mathematical definition, and then of course then it's obvious a constant B field doesn't produce any EMF. Okay, doesn't produce this electromotive force, or doesn't induce any voltage. So only a varying B field or area changing with time can produce the EMF. Okay, so what do I mean there? If you look at this equation, okay, so anything is changing as a function of time is going to give you EMF. Okay, so of course then you have some options. You say, okay, if my B field is changing as a function of time, then of course I'm going to have EMF, right? Another possibility is if you somehow say, okay, you have the magnetic bar here, you fix the magnetic bar, but you start to say, okay, we go this loop, right? You try to make it smaller, make it wider, bigger. Well, okay, you try to jiggle this loop, then you can also actually have an induced voltage. Okay, so then the textbook is giving you some examples, and such that I think that's one of the homework problems you have to do. Okay, so the first guy is, I think that's the same one we have been seeing in chapter 2, one of the figures. So the induced voltage, the EMF, in for that problem is actually this. Okay, now if you remember the equation from the previous slide, right? Okay, so let's just go back. So the flux is defined by the integral of the B field over the area, and then just calculate the derivative with respect to time, and then add a minus sign. All right, okay. So then here you can see if I have a changing field like that. Okay, notice that actually the orientation, or say the direction of the field, is fixed. Okay, it has a theta away from the z direction, but it's just the amplitude of this B field is changing. So we have this B, and then multiplied by the sine omega t. Okay, so you can see that the z component of this B field, which is parallel to the normal component of the loop, right? So this is a square loop, and the area is L squared. And then we'll do the inner product with the B field, but it has to be the z component of B field. So that's B times cosine theta. So that's my flux. And then, but then I also have the sine omega t, that component, right? And then now you do the derivative. So the flux is what? L squared, and then B, and then we still have that sine omega t. Okay. And then also have the cosine theta. Okay. So this is actually the flux. Okay, so now if you take this guy and just calculate the derivative with respect to time, then of course you get cosine omega t, you got this omega there, and also have a minus sign here. So that's easy. And then and then you can work out, of course, the other two guys. All right, now what's also kind of important is then what is actually the direction of a current actually in that loop, right? Okay, so one way to find that out is you say, okay, you have to be careful about what is the direction of that B field. So that's what I wrote here. If your sine omega t is positive, meaning that omega t, let's just say omega t somehow is between 0 and pi over 2. Okay, so right at the very beginning, if this guy is positive, then your B field is pointing upward, just like it is shown in that figure. So if the B field is pointing this way, all right, so then the right-hand rule, of course, says, okay, if my field goes this way, I should have a current going counterclockwise. Okay, but remember, because of that minus sign, because of the Lenz's law, so in fact the current flows in the opposite direction. So I should have actually a clockwise current. So the induced current, in fact, flow clockwise in that figure 8. Okay, so this is what you have to be careful. Okay, but then of course when the B field is changing, right? So now let's say if this sine omega t is negative, okay, then of course you're changing the direction of the current as well. Okay, the next thing is, notice that when we calculate the EMF and we calculate the voltage, we have this frequency dependence. Okay, now that is actually from that sine omega t. Okay, so I was writing there. We have the sine omega t, and when we calculate the time derivative, then we are getting this extra omega. Okay, and that extra omega is frequency, and we will see why that is important a little bit later. And then this last figure, this figure is close to the MRI experiments, okay? Because in the MRI field, we were saying that, remember in chapter 2, we were saying that in figure A, basically that field is a linear polarized field. It is not efficient in the MRI experiments. And so what we need is actually a field like this. and which meaning that it has a normal frequency, so that field, the V1 field, is also rotating, and then it becomes a quadrature coil, quadrature feature of the RF coil. The loop, now this square loop is fixed, right? Just imagine that in the MRI design, we are not rotating any coil. The coil is always actually fixed, okay? But we are using the current to change the field. So that's why I mean the last one actually is closer to the MRI experiment or measurement. Okay, then the next thing is that we have to say a few words about this reciprocity. Okay, so what's reciprocity? Okay, now of course you have this almost 1.5 page derivation. Basically, actually, it's 1 page derivation in this chapter 7. Okay, and basically just tells you one concept. Now, just imagine that actually you have a loop. You have a circuit here. Okay, just this circuit is just a simple loop. And you have this loop, and you have currents, and then even if you just have a DC current, okay, that's fine. Then this DC current is going to produce a magnetic field. In fact, this magnetic field is not uniform. This magnetic field is non-uniform but distributed in this entire space. All right, now think about this in the opposite way. So assuming that I have some magnetic field distribution in the space, and this field distribution turns out to be identical to the situation I just described to you, meaning that I have a circuit, I have a loop here, I have a DC current flowing in this loop, I have a field distribution. Now if I don't even tell you I have a circuit here, I just have this field distribution, well, then you probably will guess, you probably say, okay, then I think there is actually a circuit here, there is a loop here, there is a DC current flowing in this circuit. Okay, so that concept, okay, the concept that you can imagine, in fact, there is a circular loop, there is actually this DC current flowing in this loop. That concept is actually reciprocity, okay, meaning that you have currents, then the currents will produce fields. Okay, you have fields, then you can imagine that actually you would have the corresponding currents in that loop. Okay, this is not Lenz's law. Okay, I'm not talking about Lenz's law. I'm already talking about Lenz's law, but this is just even for DC current. I mean, just imagine that you can you can replace your, or not replace, you can kind of just imagine that you have the field distribution, then you will have a corresponding current in the loop. So this is reciprocity, and you can go through that 1 page derivation in the textbook, and basically just tells you that. Okay, so with the reciprocity, and basically we say, okay, now I have this EMF. Okay, so basically I have a moving magnetic field. In fact, which magnetic field is moving? Well, it's actually, if I have, okay, right now let's not confuse the situation. So let's just say I have a moving magnetic field, then I would actually pick up this induced voltage. That's my EMF. So by definition, you have that part. Okay? Now, by reciprocity, by what I just described to you, if I have this moving field, I must have a current which corresponds to the distribution of that field, and then I can actually write down this equation corresponding to the EMF. Okay. So how do I actually get that induced currents? Well, okay, so that induced currents, in fact, are from these spins, okay, not from this guy. Actually, are from those spins, because we already, so at this point, what's happening is we already actually flipped all those spins onto the transverse plane. Now I have another coil, another loop, just to detect the fields of these spins. Okay, they are changing, they are moving because of the main field. They are at least they are precessing. So those magnetizations are moving as a function of time. Okay, so this is how and so that's why we have an actually induced field because of this. And then these guys actually, of course, produce currents in the loop, in this coil loop that I'm going to have the induced current. Okay, and then the question is, what's this portion? Well, okay, this portion is basically it's the B field actually in the RF coil. Okay, now this RF coil is not the transmitting coil. This RF coil is actually this circular loop or the square loop. We put it there, which has an induced EMF, and it's the corresponding B fields produced by this current. If I have some current in that coil, then correspondingly I will have this induced B field from this coil. And the point here is that but when I take this field divided by this current, then this quantity does not depend on the fields. This quantity only depends on the coil geometry. So meaning that, okay, there is a difference whether I have a square loop or I have a circular loop. This guy will be different. So this is actually the what we have for this thing. And then again, this guy, of course, is the magnetization of protons of these speeds. So, any question about this? It's a little bit, actually a little bit, I would say a little bit confusing here.
So, because of magnetization, current is induced into the coil.
Yes.
And because of that current, we are getting this B field, right?
No, wait. So we have these spins on, say, okay, first of all, we rotate these spins onto the transverse plane, all right, and then we turn off the RF field. Okay, now we have another loop which will pick up the signal due to these precessing spins, because these guys are still precessing on the transverse plane. Okay, so now what we will pick up in this coil is the induced voltage. So that's what the EMF is about. Okay. But now the only question here is in this equation. Well, then the question is how can we actually write down this equation? Meaning that, okay, originally we just have this part. We say, okay, we understand. If I have a change in flux, the minus sign in front of a change in flux gives me the induced voltage. But how am I going to write down this portion? Well, in order to write down this portion, we actually need the reciprocity. Meaning that I have to figure out what is actually the induced field through this coil. So I have the coil here. What is actually the induced field through this coil? But what's the induced field here? What the induced field, in fact, is produced by these moving spins. So that's why this guy is there. I mean, remember, originally when we calculate that the flux, we are kind of doing an inner product between the field and the area of the loop. Okay. But by reciprocity, you can say, okay, rewrite equation such that now we just consider a spatial integration over kind of the geometry of the loop and the magnetization of the basic magnetization is the spin of these protons. But then you still have to worry about this inner product. I mean, this is actually a little bit funny. Okay, so All right, but it's okay. I mean, okay, for the first time, if it's not clear, that's okay. I mean, you don't really need to appreciate this equation right now. Okay, maybe a second time you feel more comfortable when you see this. Okay, so now we can say, okay, now with that equation, now we can actually talk about the MR signal. Okay, so the first line shows you the MR signal is actually proportional to this induced voltage. Okay, now why I wrote that way? Well, that's because the induced voltage, in fact, is pretty small. And you have to go through some amplifiers to amplify the voltage. So that's why I wrote the signal is proportional to the EMF. And EMF, by definition, is this minus d phi dt. Okay, and then the first line is just a copy from the previous slide. Okay, that's by reciprocity. We can write down something like that. Okay, now the next line is just trivial because, again, we just say, okay, for that, so that's really not a B field. It's kind of the B field per unit current. Okay, so it's a B field per unit current, and then you also have the X component, Y component, and Z component. So you write them out, but remember, just divide by this current. And then you say, all right, now let's just consider the transverse plane. Okay, so you just again rewrite the equation like this. Now remember, just from your chapter 4, and your X component of the magnetization and the Y component of the magnetization can be combined as the transverse part of the magnetization, and then with the T2 decay, and then you also have a cosine portion. Okay, that's your omega naught T and minus this phi naught component, which is a constant. And then this guy, this theta B, is basically from this Bx and By component. Okay, that's just say, okay, you have some vector dependence, or say the projection component onto the X direction and Y directions, and then you can write that also in terms of the transverse component, and so you can put the equation like that. And so that's just actually simple math. I mean, I make this complicated insane. And then you cap your Z component like that. Okay, now so why do we separate the Z component from the X and Y component? Well, that's because the next thing we are going to calculate the derivative of this whole thing. Okay? And so what's magic about that? Well, okay, so what's magic about that is when you calculate this first guy, okay, now so don't worry about this one, right? So if you apply the derivative on this, you just get 1 over T2. Okay, now remember in chapter 4 I said, okay, what's the order of magnitude for T2? It's about, for most, say the biological tissues or liquids, it is about 100 milliseconds. So 1 over T2 gives us what? About 10 hertz. Okay, so, but then the next guy is if you apply the derivative onto this cosine term, and then all of a sudden, okay, then you turn this cosine into sine, right? And then you got the frequency, this omega naught, in front of the equation. Okay, so then you say, oh, yeah, what is this omega naught? Well, this omega naught is 2 pi times the frequency, and frequency, if I'm looking at 1.5 Tesla, that is actually 64 megahertz. So 1 over T2 is 10 hertz, and omega naught is 2 pi times 64 megahertz for 1.5 Tesla. So you can forget about the 1 over T2, that term. Okay, that term is gone. Okay, and then how about the Z component? Okay, the Z component, again, remember this from chapter 4, right? So what's the solution for that Z component? Just from the Bloch equation, from the simple Bloch equation, if I have a T1 recoil, or you have a T1 in the equation, well, okay, as I said, your T1 recovery is just like you are charging a battery, right? So you always actually have this exponential minus T over T1 involved. just like your T2 decay, you always actually have this guy involved, except that you do something like 1 minus this term, right? Okay, so when you have this exponential term involved, again, you try to calculate the derivative of this guy. What are we getting? Well, we're again getting 1 over T1. And again, just from chapter 4, and we said, okay, roughly speaking, what's the value of T1 for most, let's say, biological tissues and also liquids? Well, T1 is about 1 second, on the order of seconds, and 1 second. So the inverse of that is only 1 hertz. Okay, so again, this term, the derivative, the time derivative of this term is just too small compared to that guy. So you can also forget about that. So at the end, basically this is kind of the equation for the MR signal that we are going to use. Okay. Now, of course, you have to be careful. Okay, so now let's say, hey, if you try to design a magnet which runs at the Earth magnetic field, for example, well, then you have to go back to this equation and say, oh, okay, now you have to actually worry about the T2 contribution from there. You also have to worry about the T1 contribution, okay, meaning that from the Z component of the of your spins, you have to worry about those signals as well. Okay. But right now, just in this class, and also basically in the regular MRI machines, we don't worry about the Z component, and so that's why we say, oh, okay, actually the signals are pretty much from the transverse component of these spins. Okay, so again, I said this maybe 10 minutes ago, said if you have these spins originally pointing toward the Z direction, and then you rotate these spins not completely onto the transverse plane, right? So if we do this, if we really flip all these spins onto the transverse plane, this flip angle is 90 degrees because, from here to here, it's 90 degrees. But if you don't flip these spins by 90 degrees, so let's just say you just rotate these spins by 30 degrees, okay, 30 degrees away from the Z direction, then this transverse component, of course, then you take the original M naught, the original magnetization, multiplied by sine 30 degrees. Okay. So that's where this the flip angle comes in this equation. Okay, now another kind of important point, or right now it looks actually a small point to you, but it is actually an important point later on. Here, so back to here, right? Remember when you solve the Bloch equation, okay, so again, if you just have a simple version of the Bloch equation, and let's say, okay, you just worry about the T1 regrowth and the T2 decay, and you don't really have field inhomogeneity, then your precise frequency will just be this omega naught. That's your Lama frequency, which equals to gamma times B naught. Okay? Because remember, when you are picking up the signal, you don't have this transmitting RF coil, RF field there. Okay, we turn it off. So you don't have that. You just have actually the main field, and then you have a coil which picks up the signal from these spins. These spins are precisely on the transverse plane. But typically, actually, that's not the case. Okay, I mean, for two things. Number one is that in I think it's in chapter 9 at least. Okay, you are going to encounter the gradient field. So this frequency is not going to be your gamma times B naught. Okay, so this Lama frequency is going to be different when you have an external gradient field. Okay, that's what you're going to see in chapter 9. So when you add an external field, now I mentioned this maybe was it last time, or okay, maybe last time I said this. So if you have two spins at two different spatial locations, okay, even though they are very close within a voxel, within this body, okay, if these two spins are at two different locations, but you apply a gradient field and such that actually the fields are different at these two locations, then your Lama frequency, this precessing frequency will be different, meaning that these two spins are going to precess at different rates. Okay, they're going to go at different rates. So this actually can become a function of space. Okay, so because the external gradient fields you are adding, that's one thing. The other thing is that all these spins in chapter 25, you are going to learn the magnetic susceptibility effect. So these spins, okay, so then let's say, okay, I have different materials, and we have the magnetic susceptibility effect, and that's if that's due to the static field, and such that actually the fields at different locations will again be different. Whether or not you apply the external gradient field, that's a separate consideration. Even if you don't apply the external gradient field, you can still have the magnetic susceptibility effects or the chemical shifts but these are two different things, okay? Or could be chemical shifts due to the interactions of all those spins. So then it will also affect this guy. So meaning that this guy is not going to be a constant, it's going to be a function of space. So that's why I said, okay, if you have some background inhomogeneous fields, okay, now which can be due to the nature, meaning that due to the magnetic susceptibility effect, chemical shifts, or actually can be due to some man-made external gradient fields. Then you have to replace this omega naught by omega naught plus some kind of delta omega. And that delta omega, in fact, can be a function of space. Okay, because remember, you still have to integrate, even here, you still have to integrate this whole thing over the entire sample. So you have this actually, you have to worry about this even if you do just simple NMR experiments. Okay. Now the only good news is that normally, if you are at the clinical field strength, let's say 1 Tesla or above, then this delta omega normally is very small. Okay? This delta omega, say from the susceptibility effects or from the chemical shifts, we are looking at, say, a ppm level. Okay, it can be maybe 100 ppm, but 100 ppm it is still like 10 to the minus 4, that scale. Okay, now if you add actually external gradient fields, okay, then it depends on where you are, because at every point actually the magnetic field will be different, so it depends on where you are. Okay, and then how big is that? Well, okay, when you learn chapter 9, chapter 10, you will find that out. Yeah, then of course another little thing is that you say, well, if this guy is a function of space, when you calculate the derivative with respect to time, then well, guess what? Yeah, in theory you also have to integrate that in this big equation. Okay, so this is okay. So again, look at this. We have this additional frequency. Basically, the signal is proportional to this frequency, and that is a result of the time derivative in the Faraday's induction. Okay, then the next thing is you say, well, okay, so I have this signal. Okay, go back. So I have this signal. Then what am I going to do? Okay, so I'm just rewriting this sine component as the imaginary part of this exponential I theta b minus phi naught that stuff. Okay, and plus the I omega t. So the first line just rewrite off the signal. Okay, and then the next thing is we say, oh, okay, then we have to do the demodulation. Well, demodulation just means that, okay, see that we have that omega naught t, and that omega naught actually right now is just your gamma b naught. Okay, it's your Lama frequency. It's always called Lama frequency, but in this case, it is gamma times b naught. So the point is just try to get rid of that. Okay, try to get rid of that. Okay, so how can we do that? Well, okay, so you take your original signal and then multiply by sine omega naught plus some little frequency shift. It's a little delta omega there. And the other guy is you can do this minus cosine. Okay, so you multiply by sine component, you also multiply by the minus cosine component, and okay, these are the identities of trig function. Then you have these two equations. Okay. Now the next thing is you say, okay, I have these two things, and then I want to filter out the high frequency component. So meaning that I want to apply a low pass filter. And basically the point is just get rid of this signal. Okay, so the signal at the high frequency component here, you just filter that out. You get rid of those two, and then you are just left with this cosine delta omega t, and the other guy will be sine delta omega t. But one thing actually I suspect is this. Okay, now this is what basically the book, this chapter is showing you. Okay, what I suspect is that now if you go back, so if I go back, see that omega naught, and then in the previous slide I was telling you that, well, okay, if I have the external gradient, I have the susceptibility effect, I have the chemical shifts, then that omega naught is not a simple omega naught. That omega naught in fact becomes something like omega naught plus some delta omega. Okay, so if I have something like that, then guess what? Then when we try to demodulate the signal, then I don't need this little delta omega, right? I just actually use sine omega naught t, and then the minus cosine omega naught t. Okay, I just use that, demodulate the signal. Okay, demodulate just means these two equations, meaning that I apply sine, I multiply my signal with sine and cosine. That's called demodulation. The next guy is you have to filter your signal, meaning that get rid of the high frequency component. And so there are two processes. One is demodulation, the other guy is filter. And then there's a footnote in the book saying that, okay, now we just, with the word demodulation, we just kind of include these two procedures. Okay, one is the multiplication of the sine cosine, the other one is the filter. Okay, so now we kind of get rid of the this big omega naught, that frequency. So we are left with an equation looks like this. Okay, so that's our signal. Okay. And this actually looks like, so then you say, well, okay, actually this actually looks like a signal we would have seen in the rotating frame. Okay. So yeah, so the physical meaning is almost like, okay, the demodulation is kind of just put us in the rotating frame. Okay, so we don't see that omega naught there anymore. Okay, and then then the next. So then now you look at here again after demodulation, then we have two components of this signal, and then again we combine them together because I have the sine part and cosine part, right? So you go back here, I have the cosine part and I have the sine part, so I can combine them, and then can just rewrite the signal in terms of a complex number. So then we are back to the complex signal again. So this is kind of important because, okay, so in fact the MR signal is a complex number. It's not just magnitude, it's not just phase. In fact, it's a complex number. Any question up to this point? Okay, now this one is just to kind of emphasize and say, well, okay, now what features actually we can see from this signal, from this MR signal. Okay, so again, the first one is just a copy from the previous slide, right? And then the second Boole basically says, okay, now if all those variables are independent of space, then of course then your integral. So then you look at that integral. Okay, so if my B perpendicular, which is not a field, by the way, just remind you that B perpendicular in fact is the B field per unit current, okay, and from this receiving coil. And say the magnetization, so I have a uniform sample, so my magnetization, let's say it's uniform, and then the rest, that delta omega is also not a function of space. Well, then of course, then you know that integral is trivial, then basically your MR signal is proportional to this quantity, and that Vs is just the volume of the sample. Okay, so this is what you're going to have. Okay, now, so then in fact, guess what? You can estimate the, say, okay, what is actually the amplitude of that signal? Okay, now I don't remember whether it is in this chapter or actually it's in a later chapter, okay, which actually asks you to estimate the amplitude of the signal. Okay, but you can find out. Okay, now I don't remember the number, but I remember it's that voltage is pretty small. So that's why you really need an amplifier for that. Okay, and then now let's look at something else here. Okay, so the first thing is that the transverse component of the magnetization is what I just told you, and this is proportional to the M0. M0 is actually the original magnetization, and then multiply the sine theta. Okay, theta is the flip angle. So I'm rotating these spins, say, okay, to some flip angle theta, right? So what's the transverse component? Well, of course, it's this guy. And then back to this, say even chapter 4. Okay, remember that the equilibrium magnetization is actually proportional to the external field, I mean the main field we apply, right? That's the Curie's law. So okay, so now all of a sudden if you have this guy and then you have the original signal is proportional to that omega naught, right? And then I have this transverse magnetization. I put that together, all of a sudden you see that the signal is proportional to the B naught squared, to the square of the field. So you say, oh, okay, well, you know, that's actually important, because then you say, well, then we, of course, why we want to do imaging at higher field strength, right? Because now your signal is proportional to the B field square. I mean, this is the main field. But in chapter 15, you will learn that actually the noise is also proportional to the main field strength, B naught. Okay, so such that the signal to noise ratio, meaning that you take the signal divided by the noise, you'll find out that the signal to noise ratio is actually just proportional to B naught, okay, not B naught squared. Okay, so this is actually important. If we just talk about the signal, which normally we will not just talk about signal, normally we will talk about the signal to noise ratio, okay, but you will learn this in chapter 15. So, but if we just talk about signal, then signal is proportional to the square of the field. Okay, but the signal to noise ratio is proportional to the B field. So again, the comment is this is the reason why people want to have high field machines. Okay, because with a high field machine, your signal to noise ratio is higher and higher, which is linearly proportional to the field strength. And everything, you know, any experiments, you want to do any experiments, the signal to noise ratio is the most important thing that you need to have. Okay, and then for this relative signal strength, so if you go back to, say, this equation 610, and we find that actually this magnetization is also proportional to Okay, those quantities. Okay, now the first thing is I just noticed that actually it is proportional to gamma squared, and gamma is the gyromagnetic ratio. Okay. Then so that's the first thing to notice. I mean, other things are kind of obvious. Okay, obviously this magnetization has to be proportional to the natural abundance, right? And then S are just the spins of those of a particular nuclei. Okay, so then with that, so meaning that the magnetization is proportional to the square of the gyromagnetic ratio. Okay, so all of a sudden my signal again is proportional to omega naught times this magnetization, and so all of a sudden it is proportional to actually the cubic of the gyromagnetic ratio. Now again, that's signal. Okay, so, but remember, I already told you, okay, noise is also proportional to the frequency. So in fact, in terms of signal to noise ratio, this, the signal to noise ratio is only proportional to the square of the gyromagnetic ratio. Okay, not the cube, but it's a square of the gyromagnetic ratio. Okay, now, if I stop for a minute here, if you think about this for a minute, okay, now you may remember I made a remark in chapter 2. I said, okay, for electron imaging, what's the gyromagnetic ratio of electron compared to the gyromagnetic ratio to proton? That's almost like 1,000 times bigger, okay, for the gyromagnetic ratio of electrons. So this is where you see why this electron imaging could be possible, because all of a sudden this gyromagnetic ratio in fact is 1,000 times higher than the gyromagnetic ratio of proton. So square of that, okay, forget, so just consider signal to noise ratio. So square of the gyromagnetic ratio gives me actually increase my signal to noise ratio by almost 1,000,000 times compared to the signal to noise ratio from protons. And now, of course, again, the killer is really because you have a very low abundance of free electrons in the body. So then, all right, so meaning that this natural abundance, or either this relative abundance, in fact, is very low. Okay, so you have very low values for electrons, free electrons in the body. And so that's why the signal to noise ratio for electron imaging is very low, poor. But people have shown that you can do it. In fact, there are some clinical machines now actually to do electron imaging. Okay, this so here I'm just making some remarks about the very last section, subsection in this chapter. Okay, that talks about some RF field effects and I think some phenomena, and then there's a homework problem. Okay, now I don't remember whether you are getting that homework problem or not, but I just try to explain the concepts here. And okay, so generally speaking, if we have a larger transmit field, okay, meaning that this is the field you learn in chapter 3. So meaning that I have these spins pointing to the main field direction like this. You apply this RF field, say this direction in the rotating frame, then these spins will be flipped onto the transverse plane. Okay, and this is actually my B1 transmit field. Okay, so that's why I wrote up to 90 degrees, up to here. This gives me actually the maximum magnetization on the transverse plane, right? Okay. So by reciprocity, actually it is the same for the receiving field. Okay, so that's called the B receive. So again, by reciprocity, just basically it's this. Now I have these fields, I have these spins on the transverse plane, so I can imagine the corresponding induced voltage or the corresponding induced current in the loop will also be maximum. right? So if that's by reciprocity. So that's why if you, in general, if you have a larger transmit field or you have a larger receive field, then actually you will have actually brighter images. Okay, so in MR, the larger, the higher the signal, the brighter the image. So that's basically how the MR images actually will look like. So then, of course, the smaller B1 transmit field or the smaller receiving field is going to lead the dark images. Okay, and then next thing is that now you can imagine, so then actually it's important to obtain a uniform B1 field. Okay, so why is that? Well, okay, just for the first two remarks, just imagine if I design, so even just let's think about the transmitting field, right? So here, so let's say I have this B1 field, I have this RF coil, and I apply this B1 field, but then say at this location, these 5 spins will be flipped at 90 degrees really on the transverse plane. But at this location, so I have the other 5 spins, but these 5 spins actually will just be flipped by, let's just say, 60 degrees. Then, of course, I have less signal from these guys compared to these guys. Okay, so that's why, of course, they say, okay, I want to have a uniform image, uniform intensity of the image, then I need to have a uniform B1 field. So that's obvious, but actually this is challenging. Okay, why is that challenging? Well, if you think about this, you say, oh, okay, I just start with a circular loop. Okay, I start with a circular loop, and you all know this. Okay, you this. Well, okay, you may or may not have done the calculation of, say, the field distributions from a circular loop. Okay? But at least from the freshman physics, you know that, the field at the center of this loop, actually you can calculate from the Maxwell equations. Okay, you did that probably at your freshman physics. The next thing which you probably did not do is you probably say, oh, okay, then what is actually the field distributions actually at any given point in a space? Okay, but even though you didn't do that before, but at least you know the Maxwell equations. Okay, you remember that actually it's a big interval of this current and the geometry of the loop, and okay, you have to calculate this big integral. Okay, then even though you don't know how to calculate, that's fine. I mean, you can imagine that actually this field distribution is a function of space. So it's not uniform. The point is that field distribution is not uniform. So how are you going to actually design a uniform B1 field, which has to be, so the B1 field needs to be a constant at every spatial point. So that actually has been a challenge actually in MR. And this is actually not trivial, because there was somebody, okay, I don't remember this history, but there was somebody who in fact predicted that MR would not work because you couldn't have a uniform B1 field. The reason was what I just mentioned to you. You just have a single coil like this, and you don't have a uniform field distribution around this coil. And so it really took some genius to invent what we now call the birdcage coil. Okay, so its coil looks like actually a birdcage. So if you really draw it, it's really a coil. Just look like this. So you have current flowing, say like this, and then goes around this one, and then also you have a end ring here. So this is what they call the birdcage coil. Now you can look at there's a drawing actually in chapter 27. Okay, you can look at that. Okay, so we really actually took some genius to design that birdcage coil such that now if you really take the Maxwell equations and do the calculation, meaning that if you have sufficient number of what we call the legs in this birdcage coil, you will discover that it will produce actually a uniform B1 fields inside this coil, and when you actually impose this sine omega t distribution of the field, then actually this field becomes a quadrature field, so meaning that you will rotate precess inside the bottom of this coil. So it was really because of the invention of this birdcage coil such that the MRI images actually look very, very nice. Okay, you look at those images from 1.5T, they all seem pretty smooth. Well, of course, you are seeing intensity variations. That's because we have the different T1, T2 of the bodies, right? And also have different spin densities for each tissue. So this is actually very important, to have a birdcage coil, and then such that we can have a uniform B1 field. Okay, so and the last remark is that again, I'm just kind of repeating there. The signals due to the transmitting coil is complicated because remember, I kind of just described this. This is just from the hardware point of view, okay? But you still have one problem, that is actually your block equation. So if you have, say, okay, now even if we can design a uniform B1 field, actually just say from this my hardware, well, just from the block equation, if you have a whole bunch of spins, say originally pointing to the z direction like this, and you apply this B1 fields, and you will find that, and then, okay, then let's say if you just want to do a section of image, you mean that one slice, well, you are going to find that from the block equation, when you solve the block equation numerically, and you look at the slice profile, you are going to see that actually it's not a nice rectangular shape profile we are looking at. And that's actually the content in chapter 16. Okay? So we're not teaching that, but I'm just giving you a flavor. Okay? That means certain things are happening, and just from these say equations you have learned so far. Okay? It doesn't need complicated equation. If you look at the block equation in chapter 16, okay, it just actually has this gradient fields in there. Okay? If you don't have gradient fields, actually then things are easier. Okay? Then you know how to solve it back to chapter 3. Okay, okay, no, I think this is the last one. Okay, so this is another actual remark. I think this phrase probably comes up actually also in this last section of this chapter. Okay, I think it talks about the independent coils. Okay, what does it mean by this independent coils? Okay, so I was showing you this birdcage design, and this is just considered to be one coil. Okay, so basically from this coil, we just have two wires coming out, and all right, and then we detect the signal and then do the demodulation. Okay, that's it. But let's say then how are we going to actually say use this to image? Well, let's just say we want to image my spine. Okay, so it runs from here to here. That's long. So then you imagine that, oh, maybe we have a big birdcage coil. Okay, that's true. In fact, inside the MRI machine, just around this big donut, in fact, there is actually a big birdcage coil. Okay, that's kind of the body coil. I mean, it's really the big one. But using that, actually, you are not getting the maximum signal from the big coil. The reason is, okay, the coil is too big. Okay, so yes, our spins are producing some signal, but the coil is too big, so such that actually the induced voltage is too low. I mean, generally speaking, if you remember the solution of the field, okay, so again, in the freshman physics, you may remember if you have a single loop coil, and you say, okay, what's the field at the center of this coil, right? Okay, you may remember actually that field at the center is actually things equal to mu now I. I mean, I is current, okay, mu now is the permeability in vacuum, divided by 2r. R is the radius, R is the radius of the coil. So meaning that the field at the center is inversely proportional to the radius of the coil. Okay, so what does that mean? It means that if you have a bigger coil with the same current, the fields at the center is going to be smaller. So okay, so this of course is a problem, right? So let's say I mentioned to you, I say, okay, now if I want to image the spine, but my current is limited, meaning that the bigger current, of course, you need a bigger power supply, right? So let's say your current is limited, and I want to image the spine. I still want to tip the spins around my spine onto the transverse plane, but then you now have a big coil, you have a big R, so your fields are smaller. Okay, so meaning that your B1 fields are smaller, such that you cannot really rotate these spins by 90 degrees, okay, onto the transverse plane. So you got a problem. So then what can you do? Okay, so then the next thing is that then you really have to figure out, say, well, okay, then maybe have some coils, flexible coils, wrap around the trunk. Okay, well, okay, that's one possibility. Okay, or actually they just line up actually coils. Okay, so you have these surface coils. Okay, again, just one big loop here. Okay, and then have another big loop there. Okay, have another big loop down there. Okay, so they lay these coils actually on the table of this scanner. So one coil here, one coil here, one coil here, one coil here. Okay, something like that. Okay, now you have actually one thing to worry, okay? Because now if you have, let's just consider if I have two coils close to each other, then what's going to happen? Well, what's going to happen is that these two coils, of course, just from the physics or engineering background, these two coils are going to have mutual inductance. Okay? So the mutual inductance simply means that I have current in this coil, then I'm going to actually induce some currents in this coil. Okay? That's the mutual inductance. And then why is that bad? Well, that is bad because if I have noise picked up by this coil, it will be transferred to the noise of this coil. So all the noise actually will basically be correlated. Okay, so that's bad. So then what do you want to do? Okay, so then what people had done was that you have to somehow, say, decouple these coils. Okay, decouple means that you try to get rid of, or say minimize, the mutual inductance between the two neighboring coils. Okay, so there are ways to do that. Okay, now, so before I get into too much further, so the point here is that the independent coils just means that you want to make no noise. Okay, so say no noise, but in the engineering term or in physics term, we just say, okay, we try to minimize the mutual inductance between these two coils. Okay, if you can do that, then these two coils are basically called the independent coils. Okay, that's the definition in this chapter. And so, and if you can do that, meaning that if you don't have, another word is that actually there is no crosstalk between these two coils, okay, no mutual inductance. If you can do that, then you can actually improve the signal to noise ratio of your images. Okay, now why is that? Well, the reason is actually kind of simple. Just imagine that if I use this coil to pick up some signal and I have some noise. Okay, noise is represented by noise is represented by some uncertainty, let's just say sigma. So this guy, so coil A gives me some noise or uncertainty sigma A, and then I have the other guy, the other coil, B coil, which also gives me actually some uncertainty sigma B. Now I want to actually just say, let me just add up these two images, okay, just like I add up two numbers, then my noise actually go up by what? If these two coils actually are independent, meaning that there is no crosstalk, no mutual inductance. So that's like these two uncertainties are uncorrelated, okay? These two noise levels are uncorrelated. In that case, from simple statistics, your final uncertainty or noise is equals to the quadratic sum of the two guys and take square root of it. Okay, so if you add, so meaning that if you add signal A plus signal B, this is actually your uncertainty, your noise, if these two guys are uncorrelated. If they are correlated, then all right, then it's not this equation, okay? Then actually it's complicated. So that's why it's important. So that's why you can, if you can make independent coils, meaning that if these two coils do not have crosstalk or they don't have the mutual inductance, then you can improve the signal to noise ratio, because the final signal to noise ratio is just this guy divided by sigma. Okay, so you know, so you know the following. You know, if sigma A equals to sigma B, and the signal SA is equals to SB, so then you just compare to. Okay, hopefully you guys can see. You just compare to this guy, right? This is your original, and if SA equals to SB and sigma A equals to sigma B, then what's this? Well, okay, then the answer is if I have square root 2 SA divided by sigma A. So you improve actually your signal to noise ratio by square root 2. So that's why if you can make your coils independent, then your signal to noise ratio will increase. In this simple case, you will increase the signal to noise ratio by square root 2. Okay, square root 2 increase is actually a big deal in MR. So all right, so back to this story about how you can say, okay, now what can you do in order to make the mutual inductance to be 0, okay, or minimize the mutual inductance between two coils. Okay, so from the engineering point of view, there are actually three possibilities. One possibility is that you just overlap these two coils, okay, but it's not an arbitrary overlapping. So let's say you have one coil here, the other coil, you just overlap like that. But you have to figure out this area such that the mutual inductance through that area, or say through each coil, in fact, is kind of 0. Okay, so you can do that, and that is actually the original way those people designed the spine coil, and they call that phase array coil. So they actually have 4 coils like that. Of course, I think they were square coils, okay, but that doesn't matter. So you have, as I said, one coil here, one coil here, one coil here, one coil there. Okay, so 4 coils, but the neighboring coils are overlapping, so like that. Now, the second method is you use a capacitor to decouple the mutual inductance between the two coils. All right, so then you say, okay, so basically you just consider say here's one loop and here's another loop, and then just between these two loops put a capacitor in there. Of course, you will also have capacitors actually here, there. So then you can actually also use a capacitor to basically get rid of the mutual inductance between those two coils. So that's the second way. Of course, related to that, you can imagine instead of a capacitor, you can replace that capacitor with an inductor. Okay, that can also do the trick. The third way is actually currently, I think that's the most popular way, is that you have so you have two coils here like that, and then they just actually put some I think some adjustable amplifiers or something on each coil, and such that they can adjust the amplifiers such that actually, I guess it's a receiver gain or something, and such that actually one coil kind of does not see the other, do not pick up the signal from the other coil. Okay, now exactly how they do that, that I don't know, but this is what people have been doing for more than a decade now. The reason the third method actually is most popular, that's because now if you say you have more coils, then you can kind of use those amplifiers to do what you want. Okay, for the previous methods, it will only work, meaning that you can only really completely get rid of the mutual inductance if you have if the coils are neighboring to each other. But if you have, say, the third coil here, then you cannot get rid of mutual inductance between, say, the first coil and the third coil. So that's the kind of the basic limitation. Okay. But even with the amplifiers, of course, there are also some problems there, as far as I know. Okay, and so the last remark is about this parallel imaging. Okay, and the reason is now you can imagine now if you have multiple coils, so instead of using the gradient coils to form the images, so now you can imagine you have one RF coil here, you have one RF coil here, and then each coil actually is going to pick up the signal actually simultaneously at the same time, right? You can just ask these two coils to pick up the signal from these two regions, and then at the end you just say, okay, now instead of taking this long, but now I just use these two coils, pick up the signals at the same time, and then I just combine the images. Okay, so you kind of just reduce your imaging time by factor 2. Okay, so this is the meaning of parallel imaging. But in order to do this, you must actually get rid of the crosstalk or the mutual inductance between these two coils. So that's the engineering behind it. Okay. Now here, we are not teaching the parallel imaging, and this is the added chapter in the second edition of the book. So that's the difference. Okay, so any questions? Okay, so let's just go back to the first slide and okay. So just kind of review, what we learned in this chapter. Okay, so we talk about the definition of flux. Okay, you probably have seen this actually in the freshman physics. And then I think actually more important than that, actually I should put down actually EMF. Okay, it is really the induced voltage. Okay, it's important in this chapter. And then we talk about the reciprocity. That's again just basically you have these spins. You have these spins already on the transverse plane, and the question is that you need to pick up the signals produced by these spins, right? But then you need this reciprocity in order to write down that equation, meaning that you say, okay, I have the flux, but how am I going to relate this flux to the field produced by these spins? Okay, so that's actually the purpose of this reciprocity. And then we go through the MRI signal, because going through this, the fourth one, the demodulation, meaning that, okay, these spins are rotating at the Raman frequency, and we try to actually multiply the signal with the sine and cosine component, and then get rid of the high frequency component. So that's the demodulation. Okay, and then after that you say, okay, now I combine the signals from the real part of the channel and then the imaginary part of the channel, and again the MRI signal becomes a complex signal. And then the fifth one is, now you have a relatively general equation for the MRI signal. Okay, now if you just consider this what they call the space limit situation, meaning that all the parameters actually are independent of space, then you have this simple equation, and then now you can actually just look at the feature of your signal and also the signal to noise ratio, and so then you can actually look at the signal strength as a function of, for example, the field strength, right? So the signal is proportional to the square of the field, but it's actually proportional to the cubic of the gyromagnetic ratio. Okay? Now, but if you look at the signal to noise ratio, which you will learn in chapter 15, then the signal to noise ratio is actually proportional to is linearly proportional to the field strength. Okay, but then it's actually proportional to the square of the gyromagnetic ratio. So it's this thing. And the last thing actually we talk about is the responses from the B1 field, meaning that you would like to have a uniform B1 field. If you don't, then of course the stronger the B1 field, up to the 90 degrees, is going to give you a brighter image, and the lower B1 field is going to give you a darker image, and then you're going to have a non-uniform image. Okay, and then you say, well, so what? Okay, so what? The problem is this. Then the radiologist cannot read images, cannot really find out, okay, where is the tumor and where is the problem of that person. So that's why this is important. And then I show you the birdcage design. You can look at that drawing in chapter 27. And then we talk about this independent coils, and that is really that really leads to the current parallel imaging, in the MRI field. Okay. So, any question for this chapter, or for the previous chapters, or questions for the upcoming chapter? Okay. Okay. If you don't have questions, then then you can hand in your homework problems here, and then and then today's we will just end today's lectures to here.